something completely different, but I hope not less interesting, namely a nuclear clock with Thorium-229. What do you need to build a clock? And in principle, you only need two things. You need a reliable recurring event, and you need a counter which just counts these events. So when you think of a pendulum clock, you have the oscillations of your pendulum, and you have some counter which just counts the oscillations, and then some clockwork which just transfers this frequency to some time. And in principle, you need nothing more for a clock, but of course, this pendulum clock has now some problems. So what do you need to build a good clock? Is in principle displayed here. So problems with the pendulum clock is that your frequency depends on the length of your pendulum, so this might change your frequency, then of course change your time measurement in the end. And when you think of some basic physics lectures, the frequency also depends on the gravitational field, so it's not universal. The same clock would run differently if you would run it here or on Mars, or in space you couldn't run it at all because it wouldn't work because you don't have any gravitational field there. So you need to come up with some different oscillator, and this oscillator should be reproducible, it should be somehow universal, and in the end your clock should be accurate and precise. And people thought about this, and in the last years, the best idea was to build an optical atomic clock. So what you use as your oscillator is you have a laser which is locked to a two-level system in an atom. So the frequency of the laser is just fixed to drive this atomic two-level system. Then you take a part of the frequency and then you simply count the oscillations of the electromagnetic field, which then in the end, where you can measure the frequency, and then you can build a clock out of this. And this makes really good clocks. So here you see one of the best atomic clocks at the moment, which is a strontium lattice clock, which is located at NIST in Boulder, Colorado. And this reaches a frequency uncertainty of 2.1 times 10 to the minus 80, which is just crazy. Because when you translate it, for example, to the distance between Earth and Moon, it would mean that you know the distance between Earth and Moon to a precision of 1 nanometer, which is just, crazy. And this precision now is only limited at the moment by external electric and magnetic fields. And the question is, of course, now, okay, can one do better? And the idea people came up with was now, why can we use a nuclear transition instead of an atomic transition for a clock transition? And people, did this, thought about this, performed calculations, and the expected frequency uncertainty one could reach would be 1.5 times 10 to the minus 19, so even one order of magnitude better. I mean, this is a theoretical value. We will see if one will get there in the end. And where do the expected advantages come from? The idea is that the nucleus is just so much smaller than the atomic shell that the influence of external magnetic fields is just smaller because your magnetic and electric dipole moments are just also 5 orders of magnitude smaller than in the atomic shell. And another really interesting aspect about a nuclear clock is that you could build a solid state clock, because in principle your nucleus, when you embed it in a crystal, should remain untouched from the crystal environment, and you could still probe it with a laser when it sits in the crystal. And this gives you some advantages because you could interrogate some 10 to the 19, 10 to the 20 nuclei which are located in the crystal versus 10 to the 4 to 10 to the 6 atoms which you are interrogating in an optical lattice clock at the moment. So you have much more statistics which could make your clock even better. And now I come to some potential applications of a nuclear clock or optical clocks in general. In principle, it's nearly the same. So one obvious application is improvement of satellite navigation, because these work, of course, with the measurement of time to determine the position where you are. And the better the measurement of the time goes, the higher is the precision of your position. Then it could have applications in geodesy, because relative frequency shifts are proportional to gravitational shifts, of course, and already optical atomic clocks today can sense shifts of some centimeters in height already just by relativistic effects. Then another application would be to use some clock networks. So you combine several clocks around the world for dark matter search. And what I find the most interesting applications is the question, are fundamental constants really constant? And the funny thing here is that when you think of the fine structure constant alpha, changes in the fine structure constant alpha should be directly proportional to the differences in the Coulomb potential between the two nuclear excited states you are probing. And differences in the Coulomb potential in the nucleus can be huge. So they can be in the keV, MeV region instead of some electron volts in electronic transitions. So this to the applications. And what are now the requirements for nuclear clock transitions? So what do we need? What are we looking for? At first, we need to have laser access, and today this means we need to have a nuclear transition which is in the electron volt region. And the second thing is we need to have a small line width of the transition, which means that the lifetime of our excited state should be in the range of at least some seconds. And here in this plot, you see each dot represents the energy and the half-life of some nuclear excited state. Each blue dot is a nuclear excited state. Each red dot here is an atomic transition which is used at the moment for optical clocks. And what you see here, you see this blue bar here, which is the ground state transition from the first excited state in Thorium-229, which is rather located here in this optical clock transitions than in the nuclear transitions here. And what you also see in this plot here is that while all the others are dots, because they are so known precisely, Thorium-229 is rather a bar, because the knowledge on the transition, on the properties of the transition are not known with high precision. And we can now take a look on what is known so far about Thorium-229, or the first excited state. So what you have, it has the lowest excitation energy of all known nuclear states. It has been measured indirectly to be around 8 electron volts, which is compared to the normal keV, MeV region in the nuclear excited state, really remarkably low. And we know some of the decay channels, so it decays via simple gamma decay, so by just emitting a photon. There, the lifetime is in the range of 10 to the 4 seconds, which leads to an exceptionally small line width of in the order of 10 to the minus 20. And it has another competing decay channel, which is the internal conversion decay, where the energy of the nucleus is just transferred to the electrons in the surrounding, and an electron is kicked out. And what is now really interesting is, at first, this decay channel is much faster, so it's 9 orders of magnitude faster in the microsecond range. And what's also interesting is that this decay channel is only possible in neutral Thorium-229, because as soon as you remove one electron, the removal of one further electron requires 12 electron volts, and this is already above the energy of the isomer, so it's just energetically forbidden to have internal conversion in the thorium ion. And this makes it later possible to just trigger the internal conversion decay in the experiment by simply neutralizing an ion, because then you have just this fast decay at hand when you can just trigger your decay in the neutralization. So this sounds like much is known, you can now ask a question, why don't you simply build a nuclear clock? And the problem is that up to today, no direct laser excitation has been achieved so far, and the main reason for this is that the transition energy is just not known precisely enough. So really, to drive this transition, you really need to build a laser which emits light perfectly at this wavelength, and also the wavelength region is delicate because it's in the VUV, and building lasers there is not so easy. So this brings me to the experimental objective. So at first, we want to learn more about just the properties of this isomeric transition. So we want to determine the lifetime of the internal conversion decay. This has been achieved within the last years. We also want to measure the lifetime of the gamma decay. And until today, no one has ever seen a direct gamma decay from the thorium first excited state to the ground state. So no one has really seen it before. All the knowledge comes from indirect measurement or now internal conversion measurement. And in the end, what we really need, what's in principle the holy grail in the Thorium-229 research, is an improved energy measurement, so that laser physicists can start to build a laser to really excite the nucleus. And yeah, this brings me now to the experiments which lead, or which hopefully may lead, towards a nuclear clock. I put them in 3 categories, so in principle past, present and future, so to say. So we have indirect measurements. So Thorium-229 is generated in the alpha decay of uranium-233. And in indirect measurements, they looked at the gamma spectra from following the alpha decay and just compared now lines which were populating the ground state and the isomeric state. Then we have some direct measurements. So 2% of these are then stuck in the isomeric state. So the direct measurements really look for a direct decay of this excited state to the ground state via 2% branching ratio in the uranium alpha decay. And experiments which will be in the future are some direct excitation measurements where people really want to directly excite this nuclear state. And at first I will give you some insights in the indirect measurements. So as already mentioned, there we are looking at the gamma spectrum which follows the alpha decay of uranium-233, and this gave also the first evidence already in 1976, where they concluded that there must be some level which is nearly degenerate with the ground state, but the detector resolution was not high enough or not good enough. So they concluded that there must be some excited state below 100 electron volts in 1976 already. And since then, in principle, people now try to measure this energy because it was so remarkably low. And this is how they do it, for example. So you see at this 72 keV line, this decays via one branch to the ground state and via another branch to the excited state. And they measure now these lines and take the difference of them in principle, and they get then to the value of 7.8 plus minus 0.5 electron volts. And this is the currently best accepted value. And people did this since the 90s. So indirect measurements like this in 1990, they measured a value of minus 1 electron volt plus minus 4. Then they improved the detector resolution, and they came to 3.5. And with the years, today we are ending at 7.8 plus minus 0.5 electron volts. And already this evolution shows that there's a need for a really better energy measurement because people are trusting these values. There must be something there, but no one wants to start to build a laser in principle to really do this. Which brings me now to the direct measurement. So there we want to use the isomer, just a 2% branching ratio in the uranium-233 alpha decay. So what we do, we have the uranium-233 alpha decay. This populates the isomeric state. Then out of these ions, we want to create a pure thorium ion beam. And when you remember some slides ago, as long as it is an ion, the isomer is stable, so it cannot decay fast. So it has a lifetime of at least longer than some minutes. Then we want to neutralize the thorium ions at some point. And then we know, okay, within the next few microseconds, it must decay via internal conversion under the emission of an electron. And we can then just detect the electron which is emitted during the internal conversion decay. So this is like a cartoon-like description. And this is the experimental setup we are using. So we have a thin layer of uranium-233, which is placed in the buffer gas stopping cell. This is just filled with helium buffer gas. And the recoil ions, which are coming out of the source, are then stopped and thermalized in the buffer gas. We can apply electric fields to them, form an ion beam. And this ion beam can then be purified in the quadrupole mass separator from all the daughter products which are still present in the uranium-233 source. And in the end, we can just collect our thorium-229 ions in the isomeric state on the detector. They neutralize on the detector, and then they decay directly on the detector, and we can measure the electron. And this is then what we saw when we did it the first time. So we had then the first direct detection after its prediction in 1976, or after the first indirect measurements in 1976. We were then able to really first directly detect the isomer. With some modifications on the experimental setup, we were then also able to really measure the lifetime of the isomeric state, which is shown here. So we did a comparative measurement with Thorium-230. So we had a Uranium-234 source in our buffer gas stopping cell, where we got Thorium-230 out. And you see here in the Thorium-230, we only see our ion bunch. Behind the bunch, there's nothing. And when we perform the same experiment with Thorium-229, we see our bunch, but still after that, we have a decay tail, which we attribute to the internal conversion electrons, which is really nice and led to the measurement of this 10 microseconds decay channel of the internal conversion. And of course, now you can use these electrons and measure their kinetic energy to, in the end, conclude on the energy of the isomeric state. So this is work which is ongoing at the moment. And this brings me now to the last measurement, which is the direct excitation. So the idea here is to use the Thorium-229 surface and a pulsed laser. And the idea is now, when this pulsed laser is exciting thorium nuclei to the isomeric state, what we should see is some decaying electrons after the pulsed laser. So we want to use the internal conversion electrons as a signature to see if we have excited our nuclei. And if this would be successful, we would have a first nuclear laser excitation, which would be really great, which would also be a giant step towards a nuclear clock. But here, work is still ongoing. And yeah, this already brings me to the conclusion. So yeah, I've shown you that Thorium-229 has the lowest excited state of all known nuclear levels. Laser excitation here is feasible, which is really interesting and makes also a nuclear optical clock feasible. Experimental efforts are still ongoing, and in principle, what we need is a precise energy determination. And I've shown you the concept of a nuclear clock, which poses a complementary technology and is probably highly sensitive to temporal variations of fundamental constants. And with this, I want to thank you for your attention, and I'm ready for questions.
Right, we have questions.
Yep. How much of a commercial interest is there in a clock that's even more accurate than the one we already have that you showed in the beginning?
I've no real idea about this, so I think we are in principle only interested in this. Yeah, and it's still at a real low level. I mean, no one has ever built it. We don't know how good it will be in the end, or if we can reach this 10 to the minus 19. I mean, we would expect it, but I mean, we don't know what kind of problems we will encounter on the way towards a nuclear clock in the end.
So the 229 thorium, it's radioactive still, right?
Yeah.
So how does that affect anything? You lose some.
Yeah, but I think the lifetime is some 100,000 years off. I mean, it doesn't alpha decay itself, of course, but the lifetime is some 100,000 years. So I don't know the number because it doesn't matter for us. So So it's really it's so large that it doesn't matter for us.
Okay. And the supply of uranium-233, no problem.
I mean, we got still some uranium-233 in our institute, some old uranium-233 from the 60s, which we were purifying in mines then at the institute and got back as a purified source. Yeah, I think it's from Oak Ridge from the 60s or something. That's what I heard, at least.
Okay,
yeah.
Nice. Yeah. If there are no further questions, we have one. Yeah.
Has there been a recent tendency or a trend to always improve the accuracy of the atomic clock? Have we had some, besides GPS, some other military applications? Or I mean, what are this latest tendency trend?
I mean, I think in the last 10 or 20 years, there was really a rapid increase because of the frequency coulomb technology. So you have to go back to the counter, to the clock concept. I mean, the problem always was to really count the oscillations of your electromagnetic field. I mean, to really measure precisely the frequency of your light. And yeah, with the frequency coulomb, I think, who got a Nobel Prize in 2005, I think, this really was possible, and therefore there was this steep increase within the last 20 years. So I think, yeah, every 2 years there's a new best clock, which is again a factor of 10 better, nearly. Does this answer your question? I think I missed the first part of your question.
Like, what was like the main trigger? Like, what was the main reason why you had to improve this building better from each time? Because I heard like there were some rumors that there was some, you know, like the reasons were not very ethical.
The reasons for what?
Yeah, I mean, I just wanted to know what was the main trigger for your wanting to have like every year trying to improve the accuracy.
Well, I think to just put the time measurement or just a measurement to the frontier, I think it's just probably some technological or scientific challenge to just get better. And I mean when you take a look, for example, at the fundamental constants, for example, there you have now. I mean, they can say that fundamental constants don't change with a precision of 10 to the minus 17, but I mean, you don't know if it would change at 10 to the minus 18 level or 10 to the minus 19. And I think this is probably, just to push the frontier further. This is what I think is the main reason to really do this.
Okay, let's thank Benedict again.